Hi everyone. My name is Min Huang, and today I will be presenting to you our paper called AI-based energy forecasting for net zero smart city. This work is a collaboration between me and two of my professor from RMIT University and at FT University. So the motivation of this topic comes from the global push towards sustainability and increasing critical roles in accurate AI-driven energy forecasting to achieve net zero emission. So here's the content of our work. First, we'll talk about the motivation of our work in more details. Then we'll talk about some of the techniques, the challenge, and the solutions that we have. The third section, we'll talk about some literature review, and then we'll do some comparison of some existing method, and we'll talk about some possible proposed solution and conclusion, and we'll talk about in the future work what we're going to do. So first, talk about the motivation in the global context. So to begin, let's talk about motivation first. So the transition towards the net zero smart city is no longer an option. It's like global imperative right now. So today, nowadays, the city consumes more than 70% of the world's energy, and it is account for a significant share of global CO2 carbon dioxide emission. As the urban population continues to grow, this burden is on the energy grid to become more even pronounced. So at the same time, we have rapid advancement in power electronics, including like SCI MOSFET based gate driver, which help reduce harmonics and improve power conversion efficiency. These technology are essential to support more renewable generation. So researchers worldwide, and ecologists right now are increasingly focused on innovative solutions that can simultaneously improve the sustainability, the economic resilience, and the energy reliability. So the foundational challenge of the forecasting is that one defining feature of the smart city is that it needs to manage the energy in a decentralized, data-rich, and demand-responsive manner. So at the heart of that thing lies one of the very critical problem, which is accurate energy forecasting. In traditional energy forecasting, we have traditional methods that struggle to handle fluctuation, consumption behavior, volatile renewable energy generation, or methods like weather-dependent sources like wind, solar energy, or so. So in contrast, we have the AI revolution right now. So AI techniques, both including machine learning and deep learning methods, have revolutionized the forecasting lately, since it leveraged the historical data, the weather input patterns, and real-time inputs uh, for IoT data to provide more accurate and dynamic predictions. So in this transition, I will go through some of the major techniques, challenge, and research trend right now in energy forecasting. So this section, we talk about the major challenge and some of the AI approaches that have been used for energy forecasting. We have five types: the regression-based, time series-based, ensemble-based, deep learning method-based, and some hybrid approaches. Here are some of the major challenge and solutions before we dive into each of the methods. So we have four core challenges: the data quality and availability. So energy data can be very incomplete, noisy, and inconsistent. So the solutions that we may use is to augment the data, make very careful preprocessing, and enhance anomaly detection or so. The second thing will be about scalability, where you have smart city scales forecasting, which requires an enormous data set. So we'll need to address that through edge computing and cloud-based AI architecture. Third one will be about cybersecurity risk, as AI methods are extremely vulnerable to data breach and adversarial attacks. So we need to secure the data pipeline and have some AI-driven institution protection. Finally, we'll have privacy concern and real-time deployment, as it's may collecting the data may require data projection measure, and when we deploy it to real time, the forecasting must adapt quickly to changing condition. So the solution would be to strictly provide data protection and privacy. So now talk about the literature review part. So first we'll talk about the regression based methods. So regression-based method have some core models, including simple ones like linear regressions, support vector regression, SVR, and we have some more advanced one like semi-parametric regression. So these models are used for their interoperability. They have low computational cost and provides strong short-term performances. Um, Later studies make use of the semi-parametric models that combine the linear structure with nonlinear smoothing techniques, like the path smoothing or so. These models they improve the flexibility while retaining interpretability. So they're simple, but they have a very major limitation is that they are unable to capture highly nonlinear, heterogeneous, or rapidly changing energy patterns. So here's an example of a diagram of the semi-parametric density forecasting methods that is included in one of our studies. You see that it has the three stages, modeling, simulation, and forecasting, and evaluation. Then we'll go to the next time series based approaches. This is one of the very widely used methods. So time series methods models traditional form of forecasting. We have three key methods here. ARMA for stationary series, ARIMA introducing the differences to handle the trend, which accounts for non-stationarity, and SARIMA, which is an extension of ARIMA that incorporates seasonal components, so they are effective for more periodic patterns. These models perform particularly well for short-term forecasting in system and consistent periodic pattern. However, as forecasting horizon try to increase, the uncertainty compounds and confidence interval will widen significantly. So this is an example of a ARMA solar forecasting diagram. So the study have shown that using this ARMA architecture, the RMSE can be as low as at like zero point 0.6 for solar radiation, and it has very strong performance for 24-hour ahead forecasting. These models remain very effective baseline even for like modern smart grid forecasting system. The third approach that we're going to talk about is the ensemble-based method. So ensemble-based combine multiple models to produce more accurate and robust predictions. Some of the very major types of ensemble learnings include bagging, random forest, and gradient boosting slash XGBoost. So bagging improves the robustness by training multiple models on bootstrap sub dataset. Random forest is a widely used bagging method, which is very resilient to noise and overfitting. And boosting, one of the highlight boosting method is XGBoost. They are highly valued for the high accuracy and handling the non-stationarity in the data. Their ensemble-based methods are extremely powerful with settings like heterogeneous data sort, even with missing that values data and with complex nonlinear non-relationship. So this is an example of a bagging forecasting system as we can see here. The key advantage of bagging is the variance reduction through some of the bootstrapping part, which is very crucial to volatile energy markets right here. Random forest design, as we can see here, is also very wide use. So random forest, in this example, this architecture is used for building level energy prediction, for campus energy forecasting, and even for cross-country load forecasting. It can handle the noise exceptionally well, very robust to overfitting, perform consistently across different climate zone and different building type. And finally, we have a simplified flowchart using an XGBoost diagram right here. So XGBoost builds the tree sequentially, correcting the errors of the previous tree. And energy forecasting, it consistently achieve lower RMSE, better stability, and even better performance for like EV charging or building energy consumption compared to like bagging and random forest. And in many industry nowadays, XGBoost is still one of the strongest non-deep learning baseline and is still being benchmarked. So now we'll talk about some of the deep learning based methods. So deep learning based methods have overcome the limitation of classical method by automating the learning feature. Some of the key architecture that we'll talk about in this case are recurrent neural network and some of the advanced variants like LSTM, GRU, and even better some transformer-based methods. So these models they can handle long temporal dependency. They have high in dimension inputs with nonlinear consumption pattern, and they are able to do real-time forecasting. So example, we can see that GRU base has very strong performance in predicting, for example, hourly power consumption for ESS system. So you see here's an example of a GRU-based system for smart building prediction. So sometimes GRU can over and outperform LSTM in energy forecasting due to its simplicity. It has fewer parameters, faster training time, and better generalization. And many studies have shown that. Finally, we'll talk about the hybrid approaches. So hybrid approach meaning that we are combining the strength of multiple techniques, such as, for example, CNN with LSTM with attention mechanism or other ensemble strategies. So some of the example we see includes, for example, bagging combined with SCN neural network, CNN, LSTM attention mechanism, GRO plus attention mechanism hybrids. This model can achieve state-of-the-art accuracy across multiple renewable forecasting, binary diagnostic, or smart grid application. However, since they combine multiple different complex architecture with each other, they will have very high computational complexity, so making them for real-time deployment even more challenging. Here's an example of a hybrid approach of bagging and SCN diagram. This design demonstrates an ongoing trend of combining traditional time series such as bagging with deep learning architecture of a neural network to extract features, and sometimes you also include the attention mechanism to capture longer range pattern. Here's another example of the GRO attention architecture where you have multiple GRU going through the attention layer before going to a final um, linear deep learning DNN and give us the output. So that's an overview of the 5 different types of approach that we talk about right here. Here's a summary of the existing method that we have talked about. We have regression-based method, which is integratable but limited to nonlinear system. We have time series. They are strong for seasonal pattern but weaker for longer term horizon. We have ensemble-based method. They are highly accurate, but they are extremely computational extensive, and they also reduce the interpretability because we're gonna need careful hyperparameter tuning. Yep. Machine learning and deep learning based method, they are excellent for complex data but would requires a lot of data set with many hyperparameters. Finally, we have hybrid methods. They will achieve state-of-the-art accuracy with best performance, but they are very high complexity, even more computationally demanding. This comparison shows that why many modern universities increasingly rely on deep learning or hybrid-based method, especially when dealing with like renewable energy sources. So, in conclusion, we see that AI technology plays a critical role in achieving net zero goals by enabling accurate energy forecasting, proactive grid management, or optimized renewable integration, and even for efficient urban energy planning. So our review right here shows us why hybrid and deep learning method currently provides the best forecasting performances, especially in environment with high uncertainty. So in future research, we're gonna focus on 4 promising direction: decentralized management using blockchain, adding explainable interpretability techniques of explainable AI may improve with federated learning, and we may also integrate more smart manufacturing by connecting energy forecasting with robotics, automation, and industrial system. They are extremely helpful for the next generation's net zero smart city. So here are some of the references that we use in our work. This is not all, but some of the highlighted one. So if you have any other questions, let me know. But right now, thank you for listening to my presentation.